So in this section, we're going to talk about three things. How do we solve repeated roots for the characteristic equation? How do we deal with higher order differential equations? Can we apply the technique we've been learning to like a third order or fourth order? And then this idea of reduction of order. Now, if you're watching this video, I'll tell you right now, the whole section on reduction of order, you can kind of skip it. There'll be one or two homework questions on it. Very rarely do we ask exam questions on it. It's just kind of a justification for something that we get with repeated roots. I would not, and I highly advise this, would not spend hours upon hours doing reduction of order because at the end of the day, it's not that important. It's just something that exists for us to justify how we get an answer, which you'll see in a little bit. So, if you don't study it too much, I promise you, you'll be perfectly fine. So, let's get into the repeated roots aspect first. So, one of the things we have to talk about is what does it mean to be a repeated root, at least from an algebraic perspective. So, the algebraic multiplicity, which is often abbreviated as AM, of a root to a polynomial is the value k such that uh, x minus r to the k power is equal to 0. So essentially, it's the number of times a root will appear, right? But this is a formal definition, right? X minus r to the k power. So for example, if you have x minus 3 to the fourth power equals 0, what I am saying is that x equals 3 appears 4 times. So the algebraic multiplicity is 4. So you would say algebraic multiplicity, that's equal to 4. Knowing the algebraic multiplicity has a lot of important information regarding the solution of polynomials. In linear algebra, we use this when we're talking about eigenvalues and eigenvectors, which we'll actually talk about in chapter 7. But some other things that can tell you the behavior. For example, in this class, when we did 2.5, which was population dynamics and stable versus unstable and semi-stable, generally when you have a polynomial problem, if you have a repeated root that's even multiplicity, 2, 4, 6, 8, it tends to be semi-stable. Whereas if you have odd multiplicity, like 1, 3, 5, or 7, you'll have stable or unstable. So there's actually some information there. Graphically speaking, if you have a even multiplicity like 2, 4, 6, 8, your curve will bounce off the x-axis. It won't actually cross it. And then if you have an odd multiplicity, it'll cross the x-axis, but it'll cross it in a different way. So like multiplicity of 1, a unique root, cuts right through the x-axis, whereas like 3, algebraic multiplicity of 3, it kind of does this weird curve when it crosses the x-axis. Um, but these are just things that you just pick up on as you kind of analyze and study polynomials. Now, how does this play into differential equations? Well, I'm not going to justify where this answer comes from. You're just going to take it as fact for now. If you do watch the reduction of order, it'll make sense where it comes from. So the solution to ay double prime plus by prime plus c equals 0 when b squared minus 4ac is equal to 0, i.e. you have repeated roots, r1 is equal to r2, will be y equals c1e to the rt. It's r because r1 is equal to r2. So far, that looks just like a unique solution, sorry, real distinct roots. However, it's the second part that's a little bit different. It's going to be C2TE to the RT. So notice that there's this extra T variable right here. And if you're wondering where that comes from, it comes from the fact that without it, we would have linearly dependent solutions. And this goes back to 3.2 when we talked about the Wronskian and all that. In order for your solutions to like work properly and for you to have all of the information that you want, you need independent solutions. And without that t value, you would just have two functions that are essentially the same and they're not independent. So that's why it's there. Now, where it comes from, we have no idea yet. It's a reduction of order thing. But for now, and it's just easier to take it as fact while you're just kind of learning how to solve these problems. And then eventually it starts to kind of make sense on like why we need it. But for now, just take it as this is just the reality of the solution. So if you're wondering, what do I need to know to do well on the exam? Just memorize this formula for repeated roots. That's it. And if you feel comfortable with distinct roots and complex roots, repeated roots is the same thing. The same four steps that we do to solve basically all of the problems. So we're going to do an example now. So solve the differential equation y double prime minus 10y prime plus 25y equals 0. So we still follow the same four steps. Step one, formula. So AR squared plus BR plus C equals 0. Y double prime is equal to R squared. Y prime is equal to R. Y is equal to 1. Step two is we're going to plug in. So we get R squared minus 10R plus 25 equals 0, right? And it's at this point where you're going to, you can factor these usually if their numbers are nice. So step three is solve quadratic. If you do the quadratic formula, which I will do here just so you can see what happens when you do the quadratic formula. So R is equal to negative b plus or minus the square root b squared minus 4ac all over 2a. R is equal to negative 10. Don't forget the double negative there. Plus or minus negative 10 squared minus 4 times 1 times 25 all over 2 times 1. And then you get R equals plus or minus, sorry, forgot the 10. So negative negative makes it a positive 10. And what you end up getting is 100 minus 100 all over 2. And so then you get R equals 10 plus or minus 0 over 2. And then R equals 5. Right, so you notice that the plus or minus disappears. There's no second component that you add or subtract, and therefore you get only one answer, 5. So that means 5 is a repeated root. It happens twice, okay? So we have an algebraic multiplicity of 2. And if you're wondering, how would I actually know that? Well, there's this theorem in algebra called the fundamental theorem of algebra, which says all polynomials have n complex roots, right? So if a second order polynomial has 2 degrees, it has to have 2 roots, right? And they can be up to complex numbers, meaning if I only have one number, it has to be there twice because n polynomials have n roots essentially. So that's kind of why. So doesn't really change anything in terms of like how we solve the problem, though. It's just something we have to kind of know. So then step four is classify and plug in to solution. So now this is where kind of that decision tree comes into play. Okay, what kind of roots do I have? Okay, I have repeated roots, which means I got to use this formula, right? Now you have to think about 3 different formulas. So if you're wondering what formulas do I need to memorize for the exam, it's the repeated roots right there. Then we go all the way back. The complex root, which is right there, the e to the alpha t, c1 cosine, and sine. And then if we go all the way back to the first one that we learned, which was the real distinct root, it's going to be very shortly. Not that. It's going to be, where'd it go? Yes, I guess right there. C1 e to the R1t plus C2 e to the R2t. So that's the formula, right? And that's it. That's all the formulas you got to memorize. So for this, we have y equal to C1 e to the RT plus C2 e, sorry, don't forget the t, e to the RT
So then y is equal to C1 e to the 5t plus C2 t e to the 5t, like that. Again, a reason that t is also there is because if you have two solutions, right, two different solutions, C1 and C2, they can have different constants, but without the t, you could actually never solve for C2. You would be stuck. And so that t makes it independent, which allows you to solve for it. So that's kind of the reason for it. So that's how you solve a generic repeated roots case. No different than anything we've been talking about so far. So now we're going to do an example where we're going to have initial conditions. So we'll see how that plays out. Actually, repeated roots with initial conditions tend to be not that bad because if your initial condition has a zero in it, actually makes them so much easier. The one thing is, if you remember from complex roots and real distinct roots, we had like different cases, like I could remove something. With this problem, it has to be the same form because repeated roots only can look a certain way. The only way I can make it look is what we call the perfect root, which is, x minus r squared equals x squared. Let's see if I can do this correctly. Plus 2xr plus r squared. I don't think that's right, but might be a minus. There we go, something like that. Where it has to always look like this. Like it has to have a very specific form. No, there's a Yeah, that sounds about right. So that's the nice thing is it always behaves a certain way. Like there's no way that I can make it look different, essentially. I can make it look nastier with numbers that are just not fun to deal with, but there's no structural change. So that's kind of a nice thing. So solve the differential equation. Actually, let's just say IVP to know that it's initial value problem. Y double prime plus 4y prime plus 4y equals 0, given y of 0 equals 1 and y of 0 equals 2. And I'm also going to show you what happens if you forgot the t, like does it make a difference? And you'll see that it actually does. So step one is, okay, formula. What is the formula? AR squared plus BR plus C equals 0. Y double prime equals R squared. Y prime is equal to R. Y is equal to 1. That is our formula. Step two, plug in. So if we plug into formula, we get R squared plus 4R plus 4 equals 0. And then step three is to solve quadratic. With enough experience, you would recognize like, oh, this is a repeated root because I can kind of factor this. So this is factorable. It has a nice factoring. And so the factorization would be r plus 2 times r plus 2 equals 0. So then r is equal to negative 2. So that's my root. If you did the quadratic formula, you would get negative 2. So uh, it ends up being the same thing. So step four is solution. Okay, I noticed that I only got one number. If you only get one number, that means it has to be repeated. If you're wondering, can I get like a real root and a complex root? Not with second order, because remember, all complex roots come in pairs. So a second order polynomial has to have only two roots. So a complex has to be the only one. When you get to third order and beyond, then you can start mixing and matching like repeated roots and complex roots or, so not with the second order. Second order is very limited in what it can be. So then we have y equals C1e to the RT plus C2e, but you can't forget the t, to the RT. So then y is equal to C1e to the negative 2t plus C2 te to the negative 2t, right? That's all it is. Now, the one thing that is kind of annoying about solving for C1 and C2 with this type of problem is that you have to use the product rule. So that will be a thing. So solve for C1 and C2. So y is equal to C1 e to the negative 2t plus C2 t e to the negative 2t. The derivative is going to be the chain rule. So you
e to the negative 2t is e to the negative 2t times negative 2. So that's where that negative 2 comes into play. You just bring it down essentially, or multiply by the derivative of the exponent. And then for the product rule, it's going to be C2. You can do however you want. And then this is going to be F, and that's going to be G, and the product rule is F prime G plus FG prime. So then we get e to the negative 2t. So, well, for the sake of completion, 1 e to the negative 2t plus f times g prime. So then we get negative 2 uh, e to the negative 2t like that. And there we go. Now we just plug in our numbers, y of 0 and y of 0 for 2. So y of 0 equals 1. And let me just make sure. Okay, so this is a boundary value problem. I just realized that. So this is not an initial value problem, but just for the sake of not having to change the entire mentality, we'll just put a prime there. So put a little prime. Now that just makes the initial value. If you have two conditions and they're not derivatives, we call that boundary value. So there should have been a prime there. And so we plug in and we get 1 equals C1 e to the negative 2 times 0 plus C2 times 0 e to the negative 2 times 0. So because t is there, it just basically gets rid of C2. So then 1 is equal to C1 because e to the 0 is equal to 1, not 0, right? And then y prime of 0 is equal to 2. And so we get 2 is equal to negative 2 C1 e to the negative 0. Let's put 0 there. Plus C2, and then e to the 0 plus 0 times negative 2 e to the 0, like that. And so 2 is equal to negative 2C1 plus, now here's where people mess up all the time. E to the 0 is 1. So, but because there's a 0 inside with that times 0, they sometimes kind of lump it all together and make it all 0. So know that not the entire thing goes away, just the second term inside that bracket. So then we get 2 equals negative 2C1 plus C2. And then because we know C1 is 1, we can say that 2 is equal to negative 2 plus C2, which means C2 is 4, right? Let me give myself just a smidge more space. And so then C2 is equal to 4. And that's my answer. That is the coefficients, and then now my final answer. So set 5 solution, write it right here. And we end up getting y equals e to the negative 2t plus 4 times t e to the negative 2t. And that is how we do an initial value problem. We just plug in the value of t with 0 for each of them. Now, taking this example, I just want you to see what would happen if you forgot to add t. Like you're doing this and you just forget to write down t. And would you be able to solve for C1 and C2? Suppose you forgot t and wrote y equals C1 e to the 5t plus C2 e to the 5t, right? Like that's what you wrote down. Then, you know, y prime would be equal to, sorry, I'm looking at the wrong number, so it should be negative 2. Y prime would be negative 2C1 e to the negative 2t plus, I guess, minus negative 2C2 e to the negative 2t, like that. And we see if we can solve for C1 and C2. So y of 0 equals 1 means y is equal to C1. Sorry. 1 is equal to C1 e to the 0
plus C2 e to the 0, which means 1 equals C1 plus C2.
So we have a relationship between C1 and C2.
And then y of 0 equals 2, but prime. So then we would get 2 is equal to negative 2C1 e to the 0 plus, nope, it's a minus, 2C2 e to the 0. And so we get 2 equals negative 2C1 minus 2C2. You realize you can divide everything by negative 2. So if we divide everything by negative 2, we get 1 equals C1 plus C2.
But you have the same equation, right? Notice that 1 is equal to C1 plus C2. Sorry, incorrect. This should be a negative 1. Take it back. So you don't have the same equation, but you're basically saying this.
Can I think of two numbers that add up to 1? And can I think of two numbers that add up to negative 1?
But they have to be the same numbers, right? So what numbers add up to 1? Well, 0 plus 1. But 0 plus 1 doesn't also add up to negative 1, right? So you kind of get into a contradiction. You make a statement that's not true. And if you were trying to solve this using, like, say, systems of elimination, sorry, elimination method or substitution method, you would realize that, just using a quick elimination method, you would get 0, 0, and you would get negative 2. So you're saying 0 is equal to negative 2, which is not true. Like, that's not a true statement. So there is no set of numbers that makes this work. So that's why we have that t term, is because when they're dependent solutions, I can't solve for everything. I get a situation where it doesn't really make sense. It doesn't give me all the full picture, essentially. So that's why we kind of have to add that t component to make sure it works completely.
So that is why T is needed.
So this kind of basically summarizes the entire process of doing repeated roots. So there's really not much more beyond that, at least yet. It will become much more interesting when we have non-homogeneous differential equations, because when you have repeated roots and your non-homogeneous component, the part on the right side of the equal sign, happens to be a repeated root, then things get a little interesting and very annoying more than anything. So, but as of now, this is kind of what you're limited to in terms of repeated roots. So the next thing we're going to talk about is high order differential equations, specifically linear. So the question becomes, could I apply this process of like r squared, or can I just keep doing that for other differential equations that are higher order? And the answer is yes, you could actually just do the same process. So let a1 y to the nth derivative plus a2 y to the n minus 1 derivative plus dot 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 plus, and then you just keep going. What would it be? Actually, let's do it this way. an minus 1, and then a2y prime plus a1y plus a naught equals 0. Actually, we don't want the a naught because we're not, that'd be, yeah, like that. I think that works out fine. So essentially, we have an nth order polynomial, and now we're just going to essentially do the same thing.
So let y of n be equal to r to the nth
Power,
y to the n minus 1 degree,
not degree, sorry, derivative.
this means derivative, is going to be r to the n minus 1, and you just keep doing that until you get to the very last one. So y prime is equal to r, and then y equals 1.
That's all it is. So you do the same thing. And that begs the question then, what would the solution look like? Well, the principle of superposition says I can just add solutions together to make a super solution, right? If you want to call it that.
The solution by superposition would be y equals C1e to the R1t plus C2e to the R2t plus dot 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 plus Cn e to the Rnt.
You just keep adding until you run out. So if you have a third order polynomial, you can have up to three terms. Now, it doesn't mean you have to have all of them, but you can have up to n, right? Because sometimes things, cancel out, or you have repeated roots, which is, something, and it just depends on the problem. So, but all in all, you'll have n terms usually, at least a coefficient like C1. So let's just solve. Now, to be clear, there is not an expectation that you have to be able to solve, fourth order polynomials that are very challenging, right? The trick to this is going to be if they give you a high order polynomial, they're going to make it easy enough for you to solve using basic strategies that you should know. The big one is like they'll just factor things out. So you don't have to memorize any kind of like fancy tricks for third and fourth order polynomial, at least on the exam. On the exam, they would never ask you to solve like a third or fourth order polynomial that you couldn't do efficiently. On the homework, they could be a little bit more challenging because you have more access to information. But if you're wondering like what kind of exam type questions they would ask for this, it's ones that you could easily solve, usually with like a factory. So just to kind of ease the idea that I need to know how to solve all polynomials. Because solving high order polynomials is difficult because there's a bunch of tricks that you'd have to know, like synthetic division, rational roots theorem, and stuff like that. So we're going to solve this one here. And this is kind of like what you might see on like an exam in the sense of like difficulty, where again, they're going to make it where it's easily factorable. So we're going to solve this differential equation. It's third order because there's three primes. And so step one is going to be formula. So we just modify our formula a little bit, which is AR cubed plus BR squared plus CR plus D equals 0. Essentially, we just keep adding extra terms, right? And so Y triple prime is equal to R cubed, and then Y double prime is R squared, Y prime is R, and then Y is equal to 1. Just like that. And then step two is we're going to sub into formula. So then we get R cubed minus 14R squared plus 48R equals 0. When it comes to polynomials, the thing that makes polynomials very difficult, believe it or not, is the constant value. When there's a constant number, that's what makes them very challenging. When everything has an R value or a variable, much easier. Step three, solve polynomial. So if we solve this polynomial, we notice that everything shares an R term, so I can just factor out an R. What does this do? It converts a third order polynomial, a cubic, into a quadratic times a linear term, which I can easily work with. And then you ask yourself, can I factor this or do I need to use the quadratic formula? If you've practiced any kind of factoring, this is factorable. So it'd be R. What multiplies to 48 and adds up to negative 14? Except that should be a positive 48. 6 times 8 is 48, but negative 6 times negative 8 is also 48 and adds up to negative 14. So we're going to say that. Again, quadratic formula. If that doesn't feel nice or anything, use quadratic formula. So then R equals 0, R equals 8, R equals 6. Those are the roots of the polynomial. And then step 4 is going to be plug into solution. So y is equal to C1 e to the R1t plus C2 e to the R2t plus C3 e to the R3t. So then y is equal to, now whenever you get r equals 0, that just means the exponential part disappears, which is not a big deal. It just means we have a constant solution. The order does not matter. You could get it in any order that you want.
And that's the answer, like that.
So that's how we find the solution to a third order polynomial. And fourth order is the same thing, it's just backwards, right? So that's one type of problem we can ask you with high order polynomials. The other type of problem I could essentially ask you is I could say, hey, what if I give you solutions and I ask you to find a polynomial that works for it? Like, how would you do that? Well, that's more of like a reverse engineering type problem where you're going to have to look at the solutions that are given to you and you're going to have to think about, okay, what kind of characteristic equation does it make is kind of the idea, essentially. So let's look at an example like that where I say, um, find the differential equation for the solution set. So if I give you a set of terms, you're going to say, okay, it's for the solution set, and we'll do one that's not too bad. And we'll do this one, cosine of t, sine of t, and 1. Okay, so those are my solutions. And we start to think, okay, I need to construct a set of equations that essentially make my r squared. So basically, I'm creating the r squared equation and then I'm working backwards. That's essentially what I'm doing here. So step one is formula. Still got to know what the formula is. So AR squared. And again, you just write down whatever you're feeling. So AR squared plus BR plus C equals 0. Y double prime equals R squared. Y, sorry, not plus. Y prime equals R, and then Y equals 1. Again, if I need more in the formula, that's fine. I'm just giving myself something to think about here. And then, okay, now you got to reverse engineer. So step two is you want to construct a root for each of these, right? So find R for each solution. And so you think for a second, right?
Sorry to interrupt. We can't hear you.
I haven't been talking this entire time and there's been no speech. Let me go back then.
Okay.
We'll just start here again. So, going back to where we started with finding a solution, the whole idea here is I'm kind of reverse engineering what I have already seen into what R is going to be. So, with the number one, if you look at the last example, we notice that R was zero. But if we want to think about it a little bit more, we think, okay, Y is going to be, C1 e to the RT, right? But we don't need the constants here. We can just kind of ignore them because they're not important to this type of problem. So we'll just get rid of it. So we're going to say y is equal to e to the RT. Well, my solution is 1. Y equals 1. So then I say y is 1 and it's e to the RT. The only value that would work, which would give me 1, is if r is 0, right? So if r is 0, then 1 is equal to e to the 0t. 1 is equal to 1. So r is 0 by that extension. Or you recognize that, oh, it's 1, has to be 0 from previous experience. Same thing with sine and cosine, right? Now, the thing is with sine and cosine, we don't think of them separately. We think of them as a pair. They have to come together. So y is going to be cosine t plus sine t. Well, because we're talking about sine and cosine, we're also talking about complex numbers, which means, okay, r has to be alpha plus beta I, plus or minus, because we get two of them. And we know that the solution to this type of differential equation is going to be the whole e to the alpha t and the sine and cosine. So e to the alpha t, c1 cosine alpha t, sorry, not alpha beta, plus c2 sine beta t. So that's the solution. So then you kind of match what you have. So I don't have an exponential on cosine and sine, which means alpha is 0. Alpha is equal to 0 because there is no e to the alpha. And then I notice that beta is going to be 1 because the value inside of cosine and sine is 1. So then r is equal to 0 plus or minus 1i. So then r is equal to plus or minus I. So I have found r for each component. And then step 3, after you've done all this, is combine into a function. So combine into a polynomial. So r equals 0, r equals I, r equals negative I, like that. And from there, we are going to isolate each of basically, we're going to get 0 on every single side. So then we get r equals 0, r plus I equals 0, and then r minus I equals 0. I guess I should do it the other way. And then because they all equal 0 to each other, we can multiply them together because we're making a polynomial. So r times r minus I, r plus I equals 0. And then if I FOIL these and multiply them all together, so then I get r. Now, because you have complex conjugate, you can kind of cheat this. It's going to be r squared plus 1, because r times r is r squared. And then I times I is I squared, but it's negative I squared, and I squared is negative 1, so negative negative 1 makes it a positive 1. And then you get r cubed plus r equals 0. And then now you just convert it to a differential equation using what we already know. Now, I assumed that this was a second order, but it turns out it's a third order, which is not a big deal. I can just modify that. So then the final step, which is going to be step 4, I believe. Yep. Is write as a differential equation. So if we write it as a differential equation, then what we end up getting is r cubed plus r equals 0 becomes y triple prime plus y prime equals 0. So that's how we convert from a set of solutions to a differential equation. You reconstruct it from things you've already seen, right? Now, the one that's the most tricky is going to be repeated roots because you kind of have to know a pattern. That's what we're going to talk about here. So, for repeated roots, you're going to have the following. So, y is equal to C1e to the RT plus C2TE to the RT plus C3T squared e to the RT plus dot 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 plus Cn, if you go to the nth polynomial, nth order differential equation, n minus 1 e to the RT for algebraic multiplicity equal to n. Just to give you a quick example, if we had something like y is equal to a situation of, where is it? T squared e to the 5t, then that would imply that we have a third order polynomial because it's squared, so n is equal to, algebraic multiplicity would be equal to 3. Notice that it's t to the n minus 1. And so then we would have y triple prime, right? And then it goes on from there in terms of how it deconstructs. Now I only have one term, but I'm just telling you, like, if it's a t squared, like that's where it maxes out, then the derivative is going to be 3 because it's one less, is what I'm trying to point out in this example. So the algebraic multiplicity is one higher than the degree of the polynomial itself. So that one's going to be a little tricky just because it's not something that you're too familiar with in terms of the relationship between repeated roots and the exponential with polynomials. Now, where does this all come from is going to basically be answered in the reduction of order, but the reduction of order itself is a very kind of weird topic because it's not very intuitive at all, but it does justify where all of this comes from. So there's two levels of reduction of order. Beginning of it, I'm just going to give you a formula. Like this is going to tell you exactly where it comes from, and I'm not going to justify where the formula comes from. And then I'll do an example of how they construct the entire process. So if you're just wanting a formula that would basically create a solution, so the idea of reduction of order is the idea that if I already know a solution, could I find another solution from that? And the answer is yes, you can. So this is the basic formula, not basic, but just the formula for the reduction of order process. So I'll do it this way. If y1 is a known solution to a second order ODE, then the second solution y2 is equal to y1 multiplied by the integral of y1 squared in the denominator times the integrating factor with a negative in front of it. Sorry, a negative in front of the integral part, dx. Like that is reduction of order. And that's how you find any solution knowing one solution. So to go back to the repeated root case, so for a repeated root where y1 is equal to c1 e to the rt, right? Like that's our solution. Y2 is equal to c1 e to the rt. Okay, and we can drop the c1. We don't actually need it because it's just going to all cancel out. So e to the rt, we'll just leave it like that. So then y2 is e to the rt times the integral of e to the rt squared. And then it's going to be equal to
e to the negative.
And for us, it's going to be negative -2.
That.
And if you're wondering where that -2 comes in, this is just like a generic polynomial. And just want to make sure it makes sense. Actually,
We'll simplify it so that it doesn't have r, because I think the r is just going to make it way more annoying to deal with. Because it's going to have a, b, c, and d.
so let's do e to the,
Yeah, e to the x. Yeah, e to the t. So r is 1. So e to the t, e to the t. So the polynomial for this would have been r squared plus 2r plus 1, like that. So then negative 2x, or t, because I'm using t here, sorry. -2. And I'm just making sure this makes sense. That would be a -2. Yep. Because then they both add up to 1. -2, t squared dt.
there we go.
And if you do the computation, you get e to the t integral, and then you get e to the t squared, so that's just going to be e to the 2t. And if you integrate 2, you get e to the 2t, like that. And then when you divide the same thing by the same thing, what you end up getting is e to the t integrated by 1 dt, and then you get e to the t times t.
And that's where the t comes from, just from the reduction of order process. So
That is essentially how
we generated t from our repeated roots case. It's just this whole process of uh, reduction of order. Now, this formula is derived from a whole process that's a little confusing, but we'll try to kind of go through it a little bit here. So the process of reduction of order stems from the idea that um, your solutions are multiples of each other. That's essentially what you're saying, okay?
the solutions are multiples of each other. But we want them to be independent.
So how do we do that? Well, essentially, the idea is, well, I could just say, well, my second solution, y2, is going to be some function, we'll say u of x, y1. So it's a multiple of y1, but not by just a number, but rather an entire function, which then makes it independent because you can no longer combine them together through like combining like terms. Because if they were multiples by a number, then you could combine them. But if they're multiples by a function, then you can't combine them, which doesn't make them multiples anymore. So that's kind of the idea is like you're making them not multiples of each other. So how do we do that? Well, there's this whole process, and it basically comes down to substitution and integrating factor. So we're going to do an example from that. So let's do this. We want to find u of x to make y1 not dependent. Sorry, I should say independent. It's better. Or I should say it that way, to make y2 independent of y1. So, example. Solve for y2
given y1 is equal to e to the x for the differential equation y double prime minus 2y prime plus y equals 0. So this is the example I did above. So this is how I got this answer, t e to the t plus c. So we're going to do the entire process of it. And this is what the homework does. The homework actually makes you do it step by step. So that's kind of the nice part. So step one, okay, is you're going to set up that relationship. So set up y2 equals u of x, y1. So you're going to set up this relationship. So y2 is equal to u of x. I'm just going to use a u from now on. E to the x. That's my relationship. Then you're going to take derivatives, okay? So what I am doing is since I know a solution, I'm trying to take a second order differential equation and using a solution convert it to a first order differential equation. You can actually do that. It's kind of like in algebra when you know a root to a polynomial, you can actually use that root to divide it down to a lower degree. This is the basic principle of that. So we're going to take some derivatives. So we're going to take derivatives of y1 and y2. Or actually just y2 for now. So y2 is equal to u e to the x. Now u is a function of x. That's an important thing to note. U is a function of x. So we have to use the chain rule and the product rule. So f prime g. So u prime e to the x plus u e to the x, right? Not too bad of a chain rule. And what we end up getting is the following. We can factor out an e to the x, and we get u prime plus u. Then we got to do one more derivative because we're going to end up plugging into that differential equation. So y prime, double prime. And so f prime g, so f and g, f prime g plus f g prime, so u double prime plus u prime, right? So we take our derivatives, and through some foiling, and actually you don't have to foil, you could just factor out e to the x. And what you end up getting is u double prime plus 2u prime plus u. Nice little simplification. Not too bad. And so what we're going to do is we're going to substitute this into the differential equation. So step 3 is sub into differential equation. So we do y double prime 2 minus 2y2 prime plus y2 equals 0. So we get e to the x, u double prime plus 2u prime plus u, minus 2 times y prime 2, which is e to the x times u prime plus u, and then plus e to the x times u equals 0. And if we notice that they all share an e to the x term, right? If you pay attention to that little detail, e to the x, e to the x, e to the x, I can factor it out from all of them. And then I could just combine like terms. So u double prime and then plus 2u prime plus u minus 2u prime minus 2u plus u, like that. And if I simplify all of that, I get u double prime plus 3u prime minus 2, so just a regular u prime. And then minus u, like that. And it looks like we should have more cancellation. So cancel, cancel, cancel. Let me make sure here. U double prime plus 2u prime plus u. 2u minus 2u plus y. Oh, I see. I forgot. This should not be a prime. That's why. There we go. So that cancels out with that. Yep. And then this cancels out with that. Yeah, so these all cancel out. That's exactly what I wanted anyways. So just had a prime where there was no prime to be needed. And that's equal to 0.
So now we have this simplification, and this is where it gets weird because I'm going to do a substitution just randomly. Why? Who knows? So then we're going to do sub in. Well, it's not, who knows why. The reason I'm doing this is because I'm making it first order. It's a first order substitution. We'll talk more about first order substitutions in like chapter 6 or 7. Um, but intuitively, would I have thought to do this? Probably not. This is just something that someone thought of and we kind of realized, oh, that works. So we're going to substitute W equals U prime into differential equation. So if W equals U prime, then W prime is equal to U double prime. So e to the x becomes W prime times 0, sorry, equals 0. Now, why would I want to do this? Because if you think about this in a logical way, which again, who would have, you can actually modify this to do the following. So we can manipulate the equation to the following. So you have e to the x, W prime equals 0. Well, you can divide out e to the x. Like there's nothing stopping you from doing that because e to the x can never be 0. And you have W prime equals 0. Now I could just integrate both sides and get, C, which is what I would personally do. But they want to generalize this so that it works for anything. So what they thought of creatively, and again, this would be a little bit more apparent if the numbers were a little bit more obvious, but essentially what happens is this. You would have an extra number, so you would have W prime plus some number W. Now, in this example, because we have e to the x, we have e to the x, right? If it was a different value, there would have been like W prime plus 2W, like it would have popped out. So I kind of have to make it appear for us. So, and the reason we're doing this is so that I can do integrating factor. So using integrating factor, actually, that'll just be the next step. So we sub in this, we manipulate equation, and then step 5, integrating factor. So we get e to the, I'll just say IF for integrating factor is equal to e to the integral of p of x dx, which is just going to be e to the integral of 0 dx, which is equal to e to the c, like that. And we can just call that c. So there's our constant. So why do we do this? Well, again, if you remember integrating factor, then we can just rewrite this as d over dx times w times our integrating factor equals 0 times our integrating factor. And then we can integrate both sides. And what we end up getting is WC equals 0. Sorry, no, it's equal to C. And then we divide both sides by C, and then W is equal to 1. So now we have what W is, and from there we can do the whole back substitution now. So again, doesn't get any better. So step 6 is, okay, we sub back in. Sub backwards. So i.e. sub W into W equals U prime. So 1 is equal to U prime, like that. Step 7, we're going to integrate U prime. So the integral of U prime equals the integral of 1. So U is equal to, not T, sorry, X. like that, plus C. And then step 8 is sub into y2 equals u, y1. So y2 is equal to x plus c times e to the x. And there's our answer, x plus c. But you can let c be whatever you want it to be, right? So if c equals 0, then y2 is equal to x e to the x. And that's how we get our solution to the differential equation. Now, if you think about this entire process, at some point, you may have forgotten what the heck we were doing the whole time, because I kind of did. So our goal is to find y2, the second component of the solution to differential equation. I already know the first component. It's e to the x. So what I am doing is I am trying to find the coefficient of e to the x that is also a solution. But usually it was a number. Right now it's not a number, it's a function. So through that whole process, I figured out what this coefficient was. It was x plus c, which we could just say x if we make c equal to 0. Or c could be whatever ends up being with the initial conditions. Now, if you compare this to our auxiliary method, y double prime minus 2y prime plus y equals 0, well, we just do this, right? Just, and look at that, y2. So, do we ever really need to do this whole process of reduction of order? No, not really. But if you were dealing with a complicated enough problem where you couldn't get the solution nicely like we can with the auxiliary equation, then it's a tool that's there, right? This is one of those nasty tools that you try to avoid because you have a lot of shortcuts. But in the event that none of your shortcuts work, you could always come back to this, right? So just think about it that way. We don't have to really know how to use reduction of order. At least in this process, I mean, if you ever have to use it, you just have a formula right here. Like if you ever have to use reduction of order, you can just memorize that formula because it's the same thing. It's took that whole process and just rewrote it right there. So thankfully, it's not something that you have to worry about all too much in the grand scheme of this class.